Welcome to paging part 2. So in the first part we looked at basically what is paging and how do we do translations, and we also talked about why it's quite slow because of that double memory referencing issue. And today we're going to be looking at the solution to that problem, or at least a solution which makes that problem less prevalent. And the solution to that being translation look-aside buffers. And this is a specific part of a chip's memory management unit. No. So immediately you might be asking yourself, well, what the hell is this MMU now? I've heard of base registers and bounds registers, but I didn't know about this MMU. Well, it is just a collective term used to describe the hardware registers responsible for address translation in the CPU. Now, you will realize that with paging, the MMU doesn't look right, because with pages we don't use base and bounds registers in the same way as we did with maybe segmentation and stuff like that. We use pages and page frames. So in our previous approaches in terms of segmentation and base and bounds, this is more along the lines of what our MMU was. So now our MMU in our case just has a TLB and a page table base register. Now the TLB is the actual translation look-aside buffer that I'll explain in more detail as this lecture goes on, as well as a page table base register. So this register points to the start of the page table in memory, and the specific page table that we're talking about here is of the process that is currently being processed in the CPU. Right? The MMU is in the CPU. It's a module of the CPU, so it will obviously be performing tasks related to processing of instructions within the CPU itself. Okay, so let's just ignore what the TLB is for a moment and focus on what happens when an instruction is processed. So firstly, our CPU generates a logical or virtual address, and the MMU takes this logical value and uses the page table base register to translate this address, and this register points to the top of this process's page table like any other base register would, and then the correct page frame is fetched as a result of using this page table. So we have our CPU, we get that virtual address, we use the pointer inside the MMU to point to the correct page table, we get the correct page table, and based on the page frame number that we would have isolated in the virtual address, we can then get what page frame it is that we require to get the physical address, right? So like I say, the page frame is then used to acquire the physical address, which points to a location in physical memory. And that's how a translation would occur if we didn't consider the TLB. Okay, so how is it different? So the TLB basically stores mappings between virtual and physical addresses, but not all of them, as that would obviously be too big. It only stores the mappings that are popular. So in other words, it's a dictionary that stores mappings of virtual to physical of frequently accessed memory locations. Now the V address, or the virtual address, is the key that is used and associated with a value, which is P, the physical address. So if you ever use dictionaries before, you use a key to return some sort of value. And here, like I say again, the key is the virtual address and the value is the physical address. So it's basically a hardware cache of popular virtual to physical address translations. But let's have a look at how this affects our diagram that we've been talking about. So our CPU once again generates that logical address, but now instead of going straight through the base register or the page table base register, the MMU feeds the address through the TLB first. Now two things can happen. Firstly, a TLB hit which means that the virtual address was found within the translation look-aside buffer, or the TLB. Okay, that's called a hit. And what that would then do is, well, in a case of a hit, well, then you basically are done, right? We've returned the physical address directly from the TLB, meaning we can directly access that physical memory. But what happens in the alternate case when the key value or the virtual address is not found in the TLB? Well, then we have a TLB miss. And in the case of a miss, well, we just do what we did before. We go to the page table base register that points to the page table. The page table is then utilized to get the physical address, and the physical address allows us to access the memory. So now we have two cases, right? We have the hits or miss, and obviously if you can see when we hit, it's a lot quicker because we just directly access the memory, whereas if we miss, we have to go through all of this other process of jumping between the register to the table to the physical address and then to the actual physical memory. So how does this look in terms of our overall picture? Okay, so now our algorithm with respect to address translation is slightly more different because we need to incorporate this TLB component. And here we can see what happens. Well, on line 1, we extract the virtual page number just like we did before. On line 2, we check to see if the TLB holds the translation for this VPN. So if there's a success, then we can actually just get the physical address from that, or the translation look-aside buffer entry. So if success is true, we have the hit, and then we can just go along the process of accessing the physical memory. Firstly, we need to check if the protection bits, just like we did before though. So lines 5 to 8, we extract the page frame number from the relevant TLB entry and form the physical address and access the memory. So it doesn't automatically just give you the physical address. You still have to get it through a small process of getting the offsets and then the physical address, but it's a lot quicker. So that's in the case of a hit. In the case of a miss, well, then we simply else and then go through that long process that we described before, where the hardware accesses the page table to find the translation. And what's interesting here or unique is that once we go through that process, we then update the TLB with the translation. So let me just show you on the diagram what I'm talking about here. If we miss, if we go along this route, at the very end of this process, we update the TLB to store this translation that we've now calculated. Okay, so if we miss, we then do the calculation, or we determine the translation, and then afterwards we store that in the TLB. So for next time we don't have to do the same translation. So that's how the algorithm looks. Okay, so what is an actual TLB entry? So once again, it is that the TLB is that hardware cache of the popular virtual to physical address translations. So what does an actual translation look like? And it would look something similar to this. So a typical TLB might have 32 or 64, 128 entries, so not that many if you think of all the different possibilities that it could store. But it allows us to, or allows the hardware to search the entire TLB in parallel to find the desired translation, so that's very quick. And it not only includes the page frame number, but also some other bits, such as the valid bits, the protection bits, and an address space identifier, as well as a dirty bit. So a TLB entry looks something similar to this, which is kind of similar to what a page table entry would look like anyway. Okay, so let's do a similar example as before with respect to accessing elements of an array. Okay, so here we have a simple function where we want to calculate the summation of this array, the total sum. For the sake of simplicity, we'll pretend that the only memory accesses this loop generates are to the array itself. So we're going to ignore all the accesses to variables like I and sum, as well as to the instructions themselves. And here we can see when the first array element A0 is accessed, the CPU will load a virtual, will see a load to a virtual address 100. Just hypothetically, it's 100. Okay. So this will load a virtual address 100. The hardware will then extract the VPN from this this virtual address, and you can see here, based on our diagram, it's obviously VPN 6, and it will use this to check that the TLB, or to check the TLB for a valid translation. So is this VPN, or is there translation with respect to this VPN in the TLB already? Now, assuming this is the first time the program accesses the array, the result will be a TLB miss, right? The first time that we access this array, this TLB table will be empty and it will be a miss. Therefore, we'll have to add a new entry to our TLB, and that's what this would look like, right? I'm just going to ignore other bits, it's not necessary. So our new TLB will look like something like this, a VPN of 06 with a page frame number of 3, hypothetically. The next access will be to A1, right? Because we're looping through this sequentially. Once again, the hardware extracts the VPN from this address, which gives us VPN 6 again. And it uses that to check the TLB for valid translation. Well, some good news here, it's TLB hit. Why? Because we have a translation from VPN 6. You can see our VPN 6 is translated to page frame number 3. Now, because the second element of the array is packed next to the first, it lives on the same page which had already been loaded into the TLB, and that's why it was a hit, right? This array element is on the same page as this array element. It's not at the exact same address because of the offset's different, right? But it's on the same page. And all our TLB is mapping is between pages and page frames. So that's why we can utilize this to speed things up. Now the next access is to A0, which is on VPN 6 again, and that's another hit. And you can go through this process again as we go to then A3, and this is on VPN 7, right? You can see here. Now VPN 7 wasn't, if you go back one step, wasn't in our TLB, so that's why it results in a miss. We then load that translation into the TLB, so now we have a 7 to hypothetically 8 here, and we continue the process. Then there's a hit, then there's another hit for A5, for A6 it hits because they're still on page 7. Then A7 now we have another miss because VPN 8 wasn't in our TLB. You can see there's no VPN 8 entry here, so it results in a miss. We then load that into the TLB, and we now have a valid translation. 8 will be a hit, 9 will be a hit, and that would be our entire array. So we can see information on the same page is essentially loaded once into the TLB and accessed immediately via the TLB. And this demonstrates a concept called spatial locality. So if, like I said in first year, you would say, well, a benefit to the arrays are spatial locality. This is exactly why there is that benefit. So when we have multiple array accesses, we can see that there is an efficiency that occurs through utilizing the TLB. And this is because when we hit, we only have to access one memory location because we go directly through the TLB. When we miss, then we have to have that double access. So now with TLB, instead of it being, well, it would have been 10 times 2, because it's 10 instructions times 2 accesses each. Now it's 7 accesses plus 2 times 3. Okay, so that would be 13 versus 20. So that's obviously a lot more efficient. And thus we have a little formula here that says the TLB hit rate is 70%. So we hit 7 out of 10 times. So that's how you would calculate that. So just a little bit on locality. So temporal locality means that an instruction or data item that has been accessed recently will be re-accessed soon in the future. So this is over time. We should access the same pages again and again. That's temporal locality. Spatial locality says that if a program accesses memory at address X, it will likely soon access memory near address X. So we've only demonstrated spatial locality, but in some examples to come up later, we'll also demonstrate temporal locality. So a question you might be asking, well, who handles that process of the TLB miss? Well, there are two approaches, the first being the hardware approach, and a device called the CISC handles the TLB miss in terms of hardware. And this hardware device has to know exactly where the page tables are located in memory. The hardware would then walk the page table to find the correct page table entry, just like we've demonstrated and done. And it extract the desired translation, as well as update the TLB. And this is called a hardware managed TLB. There is also RISC. Now RISC is what is known as a software managed TLB. And just before I move on, the CISC is, I'm not going to ever ask you, but it stands for Complex Instruction Set Computing, and RISC stands for Reduced Instruction Set Computing. Now the RISC approach, which is a software approach, says that on a TLB miss, the hardware raises an exception. So this is exactly like the interrupts that we've talked about in process virtualization. And there is a trap handler associated with this exception. So the trap handler is code within the operating system that is written with the express purpose of handling TLB misses. So this is our operating system or our kernel taking over processing of TLB misses. So both of these techniques are implemented. Different architectures will apply one or the other. Okay, so that's job done, right? We've resolved all the problems in terms of segmentation through the process of using paging. We have also solved the problem of paging being super slow with the TLB, and we should be quite done, right, in terms of address translation. Well, not quite. There are a few more things we need to address. For example, let's look at a couple issues of how things are at the current point. So what happens when we've implemented a TLB paging system when a context switch occurs? So here we have process A, whose access VPN 10, and then we inserted that VPN or translation into our TLB table, and that was translated into page frame number 100, and it was valid, and there was protection, read, write, execute, stuff like that, not too necessary. And then a context switch occurs. So we shift from processing process A, and now we processing process B, and process B, it has its own address space, right? And that address space also has the same page numbers, right? Because page tables are, there's not one page table for every page. There's a page table per process, and the indexing would be exactly the same. So process B is going to access VPN 10, which is a completely different page to VPN 10 that process A accessed. And what's going to happen is that it's going to come into the TLB and be translated to another page frame number, which is correct. This 10 does point to another page frame number, but this raises a slight problem. Now, when we're doing the TLB lookup and we're seeing is it a hit or is it a miss, we can't distinguish between which entry is meant for which process. So how do I know that VPN 10 translated to page frame number 100 was for process A, or was it for process B? I don't know. So that is a problem. So that's the one problem. Another problem is page sharing. So two processes can share the same page frame. All right, process 1 is sharing physical page 100 with process 2. So when we put this in the TLB, process 1 maps this page into the 10th page of its address space, and process 2 maps this physical page to the 50th page of its own address space. So now we have another issue here, is we have duplicate page frame numbers in our TLB. Now, sharing of pages is useful as it reduces the number of physical pages in use, but when it comes to TLB hit or miss, this becomes an issue here. Okay, so how do we solve the problem? Well, it is easy solution, as all we need is just more information about the entry specifically. So what we can do is we can add this ASID field here, and it serves as an identifier or an address space identifier. So now in the TLB we have the VPN of 10, which was, when we did it, was from process A, mapped to page frame number 100, and its ASID is 1, indicating that it was like process 1 or process A in this case, and the ASID for the other page table TLB table entry is 2 for process B. So we just add an additional field that allows us to uniquely identify between these two entries. And the exact same process or solution can be utilized when solving the page sharing issue, because this would be unique. Okay. The only last problem that we need to, or one of the last problems that we need to look at, is what happens when we want to add a new entry. We need to add a new entry. Well, where do we put this new entry if needed? Which entry do we replace? Our TLB only has a fixed size, so if it's full, we need to start replacing some entries and removing old ones. So the issue here is a replacement policy. Now, in order to add new entries, a replacement policy is used, and the general idea with these policies is you want to try and minimize the miss rate and hence maximize our hit rate. And there are quite a few different approaches that you can use. LIFO, FIFO, even random has its benefits in terms of it's really simple to implement, but maybe not as good in terms of maximizing hit rate. And LRU. And LIFO is just last in, first out. FIFO is first in, first out. And LRU is what we're going to be looking at now in terms of our best solution. And LRU stands for least recently used. So the idea here is that we evict an entry that has not recently been used, and we try to take advantage of locality in the memory reference stream. So we're going to get to an example of this, which will hopefully alleviate some of your confusion. But what it requires us to do is we're going to add a register to every page frame, and it's going to contain the last time that that page in that frame was accessed. Okay? And in order to determine what time things were accessed, we're going to use a logical clock that advances by 1 tick each time a memory reference is made. And each time a page is referenced, we're going to update its register. So not only when we put things in are we going to reference their time, but also if we update them, we're going to update them with the new time. If we re-reference them, we're going to update them with the new time. So again, if you're a little bit confused, the example I'm going to do now should help it. So here we have some page references. So I'm going to reference page 7, then 0, then 1, then 2, etc. all the way to the end. And here we're going to look at how our page frame changes over time. And we're going to apply our LRU replacement policy to these page frames to our TLB, which is basically this column here, to see how it changes. Okay, so firstly we're going to access page 7, and we see obviously 7, this is the first time we're accessing anything, so our TLB would be empty at this point. Okay, and you could have seen before accessing 7, this would have all been like these white squares. So we add 7 in, and the first time step was 1, so that's why it has 1 here, because this is indicated by add a register to every page frame that contains the last time the page in the frame was accessed. So that's the 1 there. That's this is indicated in this is indicating that register value. And it's red because it's a TLB miss. Okay, and the greens will be for TLB hits. And obviously it's a miss, right? It's the first time this page was referenced. Then I want to access page 0. And now page 0 comes in here, and it's red again because it's the first time I'm accessing this page. And it came in at time step 2, so that's why there's a 2 here. Okay, so that's now been processed. Then I access page 1 again. Page 1 comes in here, it's red again. It's because it would have been a miss because I haven't accessed this page before. It's not in my TLB. And it came in at time step 3, so that's why it's a 3. Cool, so now it gets a little bit interesting. We have a 2, okay, and our TLB is basically full here, so we need to replace one of these values with this new one. So remember, it's least recently used. So what we do is we look at the lowest value here in terms of our time register or last accessed register, time last accessed. So 1 has the lowest value, so that means it was accessed longer ago than say 2 and 3. So it is the least recently used. So 2 is closer to the present, so that means it's closer to the present than 1. 3 is also closer to the present than 1. So 1 is further or older than the other one, so that's the one that we're going to replace. So we replace 7 with 2. 2 is not here, so it's not going to be a hit, right? Because it's not in our TLB. And we update it with its current time, which is 4. So you can see time is just going 1, 2, 3, 4, etc. We then get an access to 0. We want to access page 0. We see here, oh, page 0 is in our TLB. So we just update this 0 with our new time, which is 5. And it's green because it's a hit, right? Because it was already here. Then we get 3. 3 is not here, so it's going to be a miss. And we need to find the lowest value, or the oldest value in essence here, which is 3. So we replace 1 with the new page, which is 3. It wasn't already here, so it's a miss, so that's why it's red. And we update the time to 6. We then get 0 again. 0 is here, so it's going to be a hit, so that's why it's green. And we just simply update the time to 7. We get a 4. 4 is not here, so we need to replace one of these. Which one has the oldest time? That's this one here. So 7 has the oldest time, so we replace 7 with 4. And it wasn't already here, so it's missed, so that's why it's red, and we get the 8. Then we have 2. 2 is not here. We look for the oldest one, which is 6. So the smallest value represents the oldest one. We update the time now to 9, and 2 goes here. And we process over and over again until we get to the end. And you can see how this process continues going forward. And after referencing all of these pages, if you simply count all the red values, that will be the number of misses. And if you count all the green values, that would be the number of hits. And you can calculate that miss rate. Now you can apply other replacement policies in exactly the same fashion like I've done here, and those will be maybe some of your TUT questions. So just a quick look for the final slide here at what a real TLB entry looks like. So it will have your VPN, your page frame number, as well as additional components like the dirty bit, the valid bit, and your ASID. So this is just an example. We'll mainly just be focusing on TLB entries with the VPN, the PFN, and the ASID, similar to a couple slides back. Similar to, basically, this is all we really care about. But if you're interested, that's specifically what the whole entry would look like. Okay, so that does it for this second part. I hope you guys kind of understand paging a little bit better now. And in your TUTs coming up, there'll be a couple examples of you working through some of this type of thing. So if you don't understand those, feel free to ask any questions. But otherwise, yeah, thank you very much for listening.